We'll now begin Chapter 5, which deals with gases. In this first section of Chapter 5, we'll talk about gas laws and the properties of gases. And in this first video of this section, we'll introduce an equation called the ideal gas law. Let's begin by talking about a couple of important properties and characteristics of gases. We'll take a look at an animation that shows a gas in a container. And we'll talk about a couple of the differences between the gaseous state versus the solid and the liquid states. So one thing is, a gas occupies significantly more volume than a solid or a liquid. A gas typically will occupy about 2,000 times more volume than a solid or a liquid, and a gas will expand to fill pretty much whatever space you give it. Additionally, gas particles have much more kinetic energy on average compared to their solid and liquid counterparts, meaning that gas particles move at much faster speeds. And let's say that you confine a gas inside of a container like this. The gas particles can move around at pretty fast speeds that we'll calculate later in this chapter, and they might hit the walls of the container. And when they do that, they exert a force. And this force is related to what's called gas pressure, because pressure from physics is defined as being the amount of force exerted per unit area. So as you might imagine, the more collisions that occur, the more force gets exerted, and the higher the pressure of the gas. Let's talk about pressure in a little bit more detail. At sea level, the pressure of the gas particles in our atmosphere will be equal to 1 atm, or 1 atmosphere of pressure. Now, sometimes you'll see pressure expressed in other units, and a common one that we deal with is torr, so it's important to take a look at that as well and see the conversion factor for that. 1 atmosphere is 760 torr, and so you could also say that at sea level, the pressure of our atmosphere is 760 torr. And you'll be given this conversion factor so you don't have to memorize it. But it is important to be aware that there are multiple different units of pressure and to be aware that conversion factors will be given to you. And you know how to use conversion factors because we've talked about how to do that already in earlier chapters in Gen Chem. Now, pressure isn't the only important property of a gas. There are a couple of other important properties that we need to consider that are all going to be related by an equation called the ideal gas law. This is an equation that relates the following 4 properties of a gas. It's going to relate the pressure of the gas to the volume that it occupies, the temperature that the gas is held at, and the number of moles of gas. So these variables are defined as P, V, T, and N, respectively. All 4 of these variables can be related via one equation of state called the ideal gas law. It says PV equals nRT. Pressure times volume is equal to the number of moles of gas times a constant R that we'll talk about in more detail later, times temperature. As we'll see later in the chapter, this equation can also be used to find out information about a gas. So for instance, if you know the pressure, the volume, and the temperature, you can solve this equation to find the number of moles of gas, right? So if you know any 3 of these variables, you can use PV equals nRT to find the 4th. And one more thing that you can use this equation to do is see how the variables are related to one another. And that's what we're going to take a look at now in a demonstration video, where we'll discuss how changing pressure affects the volume of a gas, or how changing temperature affects the volume of a gas. We'll be able to see this in a demonstration, but then also show how you can find these relationships simply by analyzing this equation. Let's now do a demonstration that will allow us to examine the ideal gas law, PV equals nRT. This equation helps us to relate 4 important variables that define the state of your gas, right? The pressure, the volume, the number of moles of gas, and the temperature. Let's think about how these quantities can be related to one another. So instead of looking at the equation and dealing with that, let's first do some observations to see how different variables relate. We'll begin by relating volume and temperature to one another. And to see the effect that volume has on temperature, I've blown up a balloon here, and now what I'm going to do is add some liquid nitrogen into this container here. Nitrogen is a gas at room temperature, but if you cool it down to minus 197 degrees C, it liquefies, and it's very cold. So we're going to go ahead and put some of that in here. What I'm going to do now is place my balloon into the liquid nitrogen and see what happens as I cool the gas that's in the balloon. Let's take a look at what's happening to the volume of the balloon. We see that as it gets colder and colder, it shrinks and shrinks and shrinks and shrinks. So what we're able to notice here is that decreasing temperature decreases the volume of a gas. Now, what would happen if I were to take the balloon out and allow the gas to warm back up? As we take the balloon out and as the gas begins to warm up, it reinflates. The volume increases as the temperature increases again. So decreasing temperature decreases the volume, just like this. And that increasing temperature allows the volume to increase. What we say is that these two variables are directly proportional to one another. Increasing one increases the other. Now, let's see how that is represented in the equation that we have for the ideal gas law. This has the form PV equals nRT, and if we go to relate volume and temperature, we can write the equation out, and when we're comparing the two variables, I think it's helpful to have the two variables on opposite sides of the equal sign like that. If I were to decrease temperature, so we'll say we decrease T, then that's going to make the right-hand side of the equation smaller. In order to maintain an equality, we have to make the left-hand side of the equation smaller as well. Now, pressure is constant here because we're working in a room that's just at a constant 1 atmosphere pressure. So P is constant. So the only way that I can make the left-hand side of the equation smaller is by decreasing volume. So we call that a direct proportionality. I think it's really helpful to be able to recognize proportionalities like this in equations so that you can make guesses as to how variables can relate to one another without having to do a lot of calculations. Now I'm going to wipe the board and we'll next talk about how volume and number of moles relate. We'll relate volume and number of moles of gas, again using the equation PV equals nRT. Let's think about what would happen if you were to increase the number of moles of gas. So increase the value of N. How might we do something like that? Imagine if you had a balloon and to increase the number of moles of gas, you would blow up the balloon. I'm not going to demonstrate that here because to do that, I have to take off my mask, which is not allowed. So just imagine what would happen if I increase the moles of gas in a balloon by blowing it up. What happens to the volume? It goes up. So if we increase the number of moles of gas, we increase the volume. Those are also directly proportional to one another, right? If I make N bigger, that makes the right-hand side of the equation bigger. And so we have to make the left-hand side bigger. If you assume constant pressure, that means volume's got to go up too. Lastly, we could think about how pressure and volume are related. I could try to relate the pressure and volume for the gas that's in this balloon by thinking about what would happen if I were to press down on the balloon, applying more pressure. What would that cause the balloon to do, right? It's going to cause the balloon to shrink. As you increase the pressure applied, that decreases the volume. So increasing one decreases the other. This is an example of what's called an inverse proportionality. Now, how do we recognize that in a mathematical equation? We'll again write out PV equals nRT for starters. And I want the two variables that I'm comparing to be on opposite sides of the equality symbol. So I can divide both sides of the equation by either P or V, it does not matter. I'll divide both sides of the equation by P. V equals nRT over P. Now, to see how these relate, let's think about what would happen if you were to increase P. If I increase pressure, I'm now dividing by a bigger number, right? That's in the denominator here. So if I make the denominator bigger, or if I divide by a bigger number, then that's going to cause the volume to go down, right? When you divide by a bigger number, that makes the value smaller. So increasing pressure decreases the volume. That's an inverse proportionality there. Being able to recognize direct and inverse proportionalities, again, is really important in helping you to answer conceptual type questions where you're asked to determine how different variables can be related. And the ideal gas law is a fantastic equation because it allows you to relate 4 different variables that can allow you to describe the state of a gas.